Thanks, Paul. So, hi, my name's Glen Romine from the National Center for Atmospheric Research. So, I guess hitting you again from that community.
Can you hear?
Hello. Okay, I think that was Nusrat coming back. Do you guys want me to continue, or do you want to have Nusrat go ahead and go?
Then you can go ahead.
Okay, thanks. So today I'm going to be talking about predictability and prediction of high impact weather. And just to make sure that we're kind of clear on definitions here, so the difference between predictability and prediction is really we can make a prediction. So basically we can simulate a weather event, and the extent to which that prediction is skillful, then that prediction has some aspect of predictability. And when we think of predictability, we can kind of break it down into two components. So the first component of that is known as intrinsic predictability. And in that sense, what we're really looking at is the extent to which tiny errors in the initial conditions of a forecast will grow during the forecast integration and lead to divergence in the forecast solutions. And so these are primarily driven by moist processes within the model, and that error growth is essentially unavoidable within a modeling system. So no matter what we do, there are certain processes and aspects of a prediction that we simply will never be able to accurately predict because it lies within this intrinsic predictability threshold. What is more commonly encountered in actual prediction is what's known as practical predictability. And practical predictability arises because we don't have perfect representations of the true atmosphere because we have an imperfect modeling system and errors in observing and weaknesses in our data assimilation methods. And when you combine all those together, it limits our predictive capability. That said, as we get better at all of these aspects, we can move closer and closer towards this intrinsic predictability limit, although we can never do better than that limit. So again, the limitations here come from imperfect observations, and this is simply because we don't have observations everywhere. There are spatial gaps, temporal gaps. Often measurements, such as from radars and satellites, are not of things that are atmospheric state variables. And in that sense, those observations are difficult to initialize models with. And our models are, at best, a simplified representation of the true processes within the atmosphere. And those errors we can always try to make them smaller, but to some extent they're difficult to get rid of entirely. And then when we talk about how we initialize our model forecast, well, we're conflating these two imperfect observations and modeling systems together using simplified methods, and collectively these all lead to errors that is what many of us are doing research on to try to minimize. So if we think about predictability of high impact weather, really a lot of where we have skillful prediction comes from the large scales, particularly during the cool season, because the energy basically from the large scales progresses downscale towards the mesoscale and the convective scale, and the convective scale is largely a slave to the mesoscale environment that it lies within. And so if you could make a skillful prediction of the mesoscale, then oftentimes the sort of convective scale predictability aspects just sort of come along for free, which is great. And so in that sense, we can often make fairly skillful predictions of high impact weather even days in advance because of this relationship. So if we use higher resolution prediction models, we could start to make explicit predictions all the way down to the scales of individual thunderstorms, and we can even start to resolve some of the feedback mechanisms where error growth associated with that intrinsic predictability limit starts to push back upscale to where moist processes lead to changes in the mesoscale and synoptic scale forcing that provides that predictability. So let's look at a practical example of what this looks like when we have strong background synoptic forcing. So in this case, we're looking at a simulation of a convective event with 4-kilometer horizontal grid spacing. And so you can see there's a pretty well organized line of convection here. And it's a little bit, I guess you could say, mushy looking. But this comes from the fact that 4-kilometer grid spacing is kind of on the borderline of what's acceptable for high resolution explicit prediction. So if we go down to 2-kilometer grid spacing, you could definitely see more finer scale features, but in terms of the overall system placement and characteristics, very little difference from 4 to 2. And then we can do the eye test and go down to 1-kilometer grid spacing. And again, we see added detail in the 1-kilometer grid spacing forecast, but largely all the features are still in roughly the same place. We haven't really added a lot of new information by going to higher resolution forecasts. And so in this case, a lot of our predictive capability is really coming from synoptic scale forcing, and there's very little opportunity for error growth to go from the convective scale back up to large scales and to perturb this sort of large scale predictability of the system. So this is a wintertime system with strong forcing. Let's consider a summertime high impact weather event where we have weak background forcing. So in this case, we're going to use 3-kilometer grid spacing in this initial eye test. And so you can see there's a large convective system that's kind of in the center of the screen, and then there's another large convective system approaching from the northwest in the upper left corner. And so this is the simulation with 3-kilometer grid spacing, and now let's go to 1-kilometer grid spacing. Now you can see that there's quite a bit of difference in this trailing convective system, so the one that's back off to the northwest, whereas the more southern system really doesn't change position a whole lot. It's largely in the same. So this is a good example of where there's this convective feedback from the original system that's then affecting strongly the predictability of this trailing system. In this case, it's sensitive to a change in grid spacing. Now, it turns out neither of these forecasts is particularly great. So despite the agreement of the leading convective system, it's actually displaced quite a bit to the west of where the observed system is, which is shown in the lower right. Also, there's definitely some issues with the convective mode forecast back over the system that's, again, to the northwest. So largely, we see this if we look at climatologies of the predictability of precipitation systems from ensemble forecast systems with explicitly resolved precipitation. Here, these are fraction skill score, so higher values are better. And then the different colored lines here are time series of forecast skill for different rain rate thresholds, going from relatively light rain to heavier rain as we go from left to right. And so you can see that our most skillful forecasts are made during the cool seasons, so autumn and winter, whereas as we go into spring and then especially into summer, that our forecast skill tends to drop off. And this largely comes from that lack of strong synoptic scale background forcing to help provide the convective environment and the initiation drivers for where convection will form. And so I'd also like to make a pitch here for the value of why we want ensemble simulations for these types of prediction problems. So this is a somewhat messy plot, but try to work with me here. So in this case, we have ensemble sensitivity analyses shown in the color fills, and the feature to watch for will be these little red blobs. So in this particular case, we have an uncertain forecast of high impact weather in northeastern Texas Panhandle shown within that purple circle. And now, if we look at this initial condition, which is the upper left panel, we don't really see any bright red blobs, which would tell us that there's a strong sensitivity to this forecast event occurring in our initial state of the forecast system. Yet, if we look 6 hours in advance, we can see that there's now a little red patch that's appeared. And this is because some members in our ensemble system have developed storms in this area. And when these storms form, it produces enhanced moisture in the mid to upper troposphere from that convective activity. And that moisture pool is basically going to move downstream as the forecast progresses and end up over the top of our region of forecast interest over Northeast Texas Panhandle. And this is the type of flow-dependent conditional predictability that we're really looking to get out of our ensemble prediction systems. And so another benefit when we talk about these high-resolution ensemble forecast systems is that we really want to be able to get what are known as storm surrogates. So we're explicitly resolving individual thunderstorms at 3 kilometer and finer grid spacing. And we can extract information from those thunderstorms, such as the strength of the updraft characteristics. So in particular, we know that thunderstorms that rotate in the middle parts of those storm systems are much more likely to result in severe weather occurring. So high winds, flash floods, tornadoes, and hail. And so we want to take advantage of that predictive capability from these storm surrogates. And instead of basically making forecasts of individual storms, we're going to make forecasts of hazards. And so we can basically stuff this calculation into our modeling system and output it at every time step so that we can capture all the information of the storm evolution within our forecast systems. And then we can take these storm surrogate fields and basically compute probabilities of hazardous weather occurring. And so in this case, in the upper left panel, these are places in our storm simulation where we have severe storm surrogates occurring, and we can smooth those out using a Gaussian smoother in the upper right panel. And then we can combine that with ensemble probabilities in the lower left to come up with a smooth ensemble storm scale probability field in the lower right. And if we do so, again, we're using fraction skill score, so larger values are better. We can see that those ensemble predictions of storm surrogates have substantial value in terms of providing enhanced predictive skill. And so, and as we go to larger neighborhoods, we can see that that skill improves, but then we lose precision in terms of where severe storms are likely to occur in a given forecast. So those surrogates work pretty well in storm environments that the model knows how to do well, and those are storm environments that have relatively large convective instability. As we get into wintertime events that have generally lower convective instability, those storm surrogates tend not to do as well because the updraft speeds tend to be a lot smaller, and we don't see that strong updraft helicity signal. And so this is an example from a winter storm. So the observed reflectivity is on the left, and a simulation of that event is on the right. And if we look at storm surrogate forecasts for this event, we can see in those number grids there, pretty small numbers from storm surrogates, and it's offset pretty far from the storm reports that are shown in those circles. The small neighborhood is on the left, and then a larger neighborhood is on the right. So if we smooth things out a little bit, it makes things a little better, but it's still not a very good forecast. So this is a place where machine learning is really proving particularly valuable. So if we apply machine learning to the same forecast system, and instead of relying solely on storm surrogates, you can use environmental information from the forecast that adds considerable predictive skill. In fact, if you look at the difference in predictive skill when we add a neural network versus using just severe storm surrogates, so again, higher values or more skillful forecasts, you can see that neural networks can add considerable value to forecast skill throughout the length of the forecast period. So, so that's pretty encouraging in terms of getting greater usability out of our existing forecasts. So if we now try to look at what we can do if we go to shorter timescale predictability. So this is an example where we're looking at predictive skill when we use an hourly updating ensemble data assimilation system and prediction capability. So again, higher values are better. And so the predictive skill shown by the blue lines is from a mesoscale analysis system, so 15-kilometer analysis, and then making forecasts from that. And then the red and black lines show when we go to a 3-kilometer ensemble analysis and then make subsequent forecasts. And then we're looking at higher rainfall thresholds as we go from left to right. So for convective precipitation predictability, we can see added value from using a higher resolution analysis out to about 12 hours into the forecast, which is pretty encouraging. But so now let's see if we can go down to even finer scales. And I think this is the sort of area that Nusrat will be talking about. So now we're looking at 15-minute updates in a ensemble analysis system, and then trying to make forecasts. So again, higher values are better. And these are subsequent forecasts that are made every hour over time. And what you can see in these is that the forecast skill starts off pretty good in these forecasts, but then diminishes, and by an hour later, they're not quite as useful anymore, and they sort of plateau and no longer sort of, you see that sharp drop off in forecast skills. So it kind of falls back to this mesoscale predictability of the background environment, and then the convective scale information from rapid cycling tends to trail off during the first hour of the forecast. We could also see that for dynamic predictions of storm surrogate objects, that there's sort of similar behavior. There's sort of a rapid decline, and then it sort of flat lines out. And so there's this sort of background predictability, and then what can be added by storm scale predictability that's somewhat short. This is particularly evident if we go to very high resolution and not particularly well organized systems. So this is an example from a group in Japan that went to very high resolution. And so their highest resolution analysis is at 100 meters, which is third from the left. And so very high resolution analysis, very detailed. If you compare that to the observations that are on the far right, you can see this is a very accurate initial analysis relative to what's going on in observations. So, and if we look in observation space of this, we can see very small errors in the red trace, which is associated with that 100 meter analysis. These look really encouraging, that they're able to add a great deal of value in the analysis. But what happens when we go to the forecast, and boom, the whole thing kind of doesn't hold together very well. You see very rapid rise in error growth shown by the rapid increase in values in root mean squared error. And so this is somewhat discouraging in terms of our ability to add predictive value, even with the most sophisticated methods that we currently have available to us today. So this is a little bit sobering in terms of how far we still have to go in terms of being able to do this type of stuff better. So in summary, we could definitely get high predictive value on the mesoscale with current predictive capabilities. When we get down to the storm scale predictability, there's still a lot of challenges that remain. We're pushing up against the limits of intrinsic predictability, particularly when we're dealing with weak forcing environments where storms are not particularly well organized. And this is definitely a real challenge, and will continue to be a challenge for the foreseeable future. And with that, if there's time, I'll take some questions.